Hello. So this is chapter 16 in class exercise 4, problem number 1, which is F16.19. At the instant zone, and A of the rod has the velocity and acceleration shown. Determine the angular acceleration of the rod and acceleration of the end B of the rod. So what we know about this problem is we know that the end A has the velocity which is going down at 6 meters per second, and acceleration, so velocity of A is going down at this point. This is VA, 6 meters per second, and acceleration of A is 5 meters per second going down. And what we need to do is we need to calculate the acceleration of the B end of the rod. So we need to calculate the AB, acceleration of B, and also the angular acceleration of the rod. Okay, so alpha AB. We haven't yet discussed the theory for acceleration calculation, but in order to calculate these accelerations, we need the value of angular velocity of rod. So we need value of omega AB. So when this rod slides and falls on the ground, it rotates. Okay, so we need to know what is this angular velocity, this omega AB. We need to know that in order to calculate this too. Okay. However, there is no need to know the velocity of end B to calculate the acceleration. But for this example, we will calculate the velocity of NB. So we'll keep this aside for now, acceleration calculation. But first we will focus on how to calculate the velocity of B and angular velocity of the rod using instantaneous center method. Okay, so we will not make use of the same method that we have done previously. So we have solved a similar problem with the scalar analysis and vector analysis, but this time we will use instantaneous center of zero velocity. So first question is, where is the location of the instantaneous center? Even before we answer that question, let's figure out that if this height from the ground is 4 meters, if this length is 5 meters, then what is the distance from this corner to NB? Okay, so you can apply the Pythagoras theorem and you can calculate that this is 3 meters. So in fact this is 3, 4 and 5. Okay, so that's one thing. Now the next is to find the location of instantaneous center. So to find the location, we know the direction of velocity vector for point A and point B. So if we draw a position vector which will be perpendicular to the velocity vector from A, it will be somewhere here, and when you draw the position vector from B, it will go up, and the point where these two vectors intersect is the instantaneous center of zero velocity. So let's find it out. Sorry, I didn't find my scale, so I'm using my calculator cover as my scale, which I do not recommend, but yeah, this is for emergency, it's fine. So yeah, this location is instantaneous center. Okay. So at the given instant, that's the center point. If that is the instantaneous center, then this length, this vector is called position of A with respect to instantaneous center. So RAIC, and this arrow vector is called position of B with respect to instantaneous center. So RBIC. So now it's very simple. We can apply the scalar equations to calculate. First, we will calculate the angular velocity of the rod from the known velocity of point A, and then next we will calculate the velocity of B. Okay. So if I write the equation for velocity of A, then VA is in scalar format, it's omega AB multiplied by R, A with respect to IC. So it's magnitude of omega multiplied by the length of this position vector from instantaneous center to point A. We know the value of A, which is velocity of A, which is 6, and the value of, we don't know omega AB, so I can just put omega AB here. But what is this length here from this point to this point? It's same as here, right? So it's 3 meters. It's multiplied with 3. So now we can calculate angular velocity of omega, which is 6 by 3, which is 2 radians per second, and the direction is counterclockwise. What about velocity of B? So velocity of B, I'm writing it here. We can apply the same equation as omega AB multiplied by R, B with respect to IC. So once we find the instantaneous center, then rod AB is not in general plane motion, but it's in pure rotation. So everything on rod AB is in pure rotation with respect to center IC. Okay, so we can apply same R omega equation to any point on the rod. So VB, we know now the value of omega, which is 2 multiplied by this length, which is 4 meters. So this is 8, and the unit is meters per second, and it's going right. And this is the velocity of B. Very simple calculation to calculate angular velocity and velocity with instantaneous center. And if you just compare this approach with the previous approach that we have followed, this is just to give you the comparison. We have done all this exercise, like we have determined the sine and x and y components of the velocity, and then resolved the x velocity and y velocity and calculated omega and v. Compared to that, it's a similar problem, and how simple it is once we locate the instantaneous center. So always appreciate the beauty of instantaneous center method, and wherever a body is in general plane motion, if you can apply instantaneous center method to calculate velocity and the angular velocity, go for that. It will save your time. So this is the next problem. It's actually, there is no need to apply instantaneous center of zero velocity calculations in this problem, but this is something that I ask you to do yourself. So look at this disk which rotates counterclockwise, and then it goes from right to left. The angular velocity of the disk is 3 radians per second. Point A is in contact with the ground, so this is the point with instantaneous center of zero velocity. You know the radius of the disk, which is 0.5 meters. It's given in the figure. So now I have a question for you. This is just for you. I mean, it's not the part of in-class exercise. You can just practice it. Apply the instantaneous center of zero velocity method and calculate the direction and velocity of point B and point C. Okay, so try it yourself. I can give you the hint. In order to calculate these two velocities, you need to multiply the position vectors from instantaneous center to point B and point C with the angular velocity. And the position vector for point B is this line, and position vector for point C is this line. You need to calculate the length of AB from the given dimensions. Figure out how to do that. And you need to do same for point C. And I'm sure you should be able to find a way how to calculate this length from A to C. So do it yourself. Find out the lengths of these two lines and just multiply the lengths with the omega, and that will give you the velocity of point B and point C. And for the direction of velocity of point B, it's perpendicular to the position vector, that is this vector, and it goes in the direction of rotation. So it goes somewhere here, because that's the direction of rotation, right? And for point C, it's perpendicular to line AC, so it's 90 degree from AC. So this is 90 degree angle, and it points in the direction of velocity, in the direction of angular velocity.